Hello, in this lesson number 4 we are going to learn the transport layer of the TCP IP stack. The main goals of this lesson are to understand the principles behind the transport layer. So first of all, we are going to learn and study which are the functions of the transport layer. We have the TCP IP stack with the 5 layers: physical, link, network, transport, and application. Now we are here at the transport layer. So which are the functionalities that are given by the transport layer? Which are the services that can be used from the network layer? Which are the services that the transport layer will provide to the application layer? So all these things are going to be learned in this lesson. We have two different protocols in the transport layer depending on the nature of the application we want to run. They are TCP and UDP protocols. So depending if we want that all the data from our application must arrive to the destination or not, we will use TCP or UDP. In the first case, in the case we want that all the data will arrive to the destination, we'll have TCP. Otherwise, if we don't care about some packets that are lost, if we can repeat the process for asking or for sending the data, we can use UDP. In the first case, TCP, applications like the web or the email or file transferring, these kind of protocols must be sure that all the packets arrive correctly, so all of them run on top of TCP. On the other hand, for UDP, we can have video calls in real time or messages that are periodically exchanged, for example, DNS or SNMP. It doesn't matter if some of the packets are lost, we can ask for them in the future. So in this case, we can use UDP. So this is the outline of the lesson. First of all, we are going to introduce the transport layer functions. This layer is the first one that is end-to-end. It means that if we have again the TCP IP stack, physical, link, network, transport, and application, this one is the first one that is end-to-end, because up to now in the intermediate systems it was mandatory to only implement up to layer 3. So both transport and applications are specific for the hosts. And this is the reason why the transport layer is the first one that is implemented end-to-end. It gives us a transparent communication to the physical medium, uses the set of services provided by the network layer, as I told you previously, and provides services to the application layer. There is an important concept of multiplexing traffic from different applications. Since we have different protocols at the application layer, we have to multiplex these applications with the transport instance. There are two types of services. The first one is the connection-oriented service that in which it's required a previous connection. So first of all, we have to connect with the other host, with the destination host. Then we can exchange data. And after that, when we don't have anything else to send, we can release the connection. So we have 3 stages: connection establishment, data transfer, and connection release. And in this case, the connection-oriented service is implemented at TCP. The other type of service is connectionless. It's similar to IP in the sense that there is no guarantee that all the data arrive to the destination. There is no need for a connection and a release, of course, so there is only one stage data transfer. The three stages in the TCP connection-oriented services are connection establishment, second, data transfer, and third, connection release. So there must be a connection before transferring data. Well, where we can find, where is it specified? So where do we know that the transport is connection oriented or connectionless? So as usual, in the protocol field, we can find a number that refers to the payload of the IP packet. In this case, we can find a couple of numbers, 6 for TCP or 17 for UDP. If protocol field is set to 6, we can find a TCP segment. Otherwise, if it is 17, we can find a UDP data. Well, let's continue with the features of the TCP protocol. TCP stands for Transmission Control Protocol. It's a connection-oriented service for transporting in the internet. So we assure that all the packets arrive to the destination. If some packets are lost, we have to retransmit them. So at the end, we have to be sure that everyone has arrived. The PDUs are named TCP segments. So the protocol data unit, a transport layer are called TCP segments. This protocol is specified at the request for comments number 793, and it was created in the 80s, in 81. But we are currently using it, and it is expected that in the future we will continue using it. As I previously told you, the connection-oriented service has 3 stages. The first one is the connection establishment. We have to establish the connection before exchanging data from the application. This is the second stage. And finally, once we don't need to exchange nothing else, we have to release the connection. Remember that for UDP, we only have one stage, data transfer. There is no need for connection. During the connection establishment, we can store some information about the state of the entity. For example, byte counters like an SDN or our free space at the buffer, because at transport layer, we have a buffer, which is called window, in which all the segments that are received are previously stored there and temporarily store them there before passing them to the application. Okay, so it's a model based on 2 agents, client, server. The client is the host which begins the connection establishment. So the one who first requests the connection. The server is the host waiting for incoming requests. So if I want to connect with another computer and I send a request, I'm the client and it is the server. We can exchange data after that, and then any one of the 2 can release the connection. So it doesn't matter that the client must be the one who disconnect first. No, it can be also the server. The concept of establish and release connections, the function, the concept of multiplexing that we will see later with the socket. The socket is the combination of an IP address and a port. The management of data exchange with applications. So if we go back again and we draw the transport and application layer, if we receive something on our buffer, imagine this is a buffer of 4 kilobytes. If I receive a segment, a transport layer with the TCP protocol, for example, I will store the segment here and here and here. And the application will ask me about the TCP entity. Okay, I can read up to a couple of kilobytes. This is a request from the application to the transport, and these two first kilobytes from the buffer are passed to the application layer and removed from the buffer. So in this case, I have 3 slots that are free for continuously receiving segments. Another function that is important is the error control by means of retransmission of locked segments and dropping duplicated segments. Okay, each segment will be identified in order to know if it has arrived correctly to the destination or not. So the process is as follows. Imagine this is a host A, host B, time goes from up to the bottom. This is a TCP segment that is sent with ID number 1. For each segment with data, I'm waiting for an acknowledgement, an ACK. If the time passes and I don't have this ACK, I have to retransmit it again, because number 1, as well as the others, must arrive to the destination. Buffers management, as I previously told you here. This is the concept of flow control. For example, imagine I'm this host, I'm receiving segments, my buffer is full, and I cannot accept more segments. I have to use a specific method to say the other, okay guys, stop sending me more segments because I cannot handle them. I'm full. Sorry, but you have to wait. This is the concept of flow control. And there is another concept, congestion control, that is related to the network, to the possibility of congesting in the routers and a mechanism to be able to act in that cases, but we will see it later. Finally, we are going to understand which is the segment format. Okay, a segment, a transport layer, has a TCP header and the payload. This is the format of a TCP segment. And then this TCP segment is encapsulated inside an IP packet with an IP header. This is the payload of an IP packet at the network layer, but this payload is a TCP segment. So now we are going to learn which are the fields of the TCP header. So we have a header of at minimum 20 bytes. Maybe the most important fields here are the source port and destination port of 16 bits. So the range is from 0 to 65535. I had to say bytes, but not they are not bytes. Sorry, I'm going to repeat it again. 16 bits for source port and also for destination port. We have the range from 0 to 65,535. This is the range for ports. And with this number, we will be able to know which is the application protocol. Then we have another different field called sequence number that identifies the segment in order to know if the segment has correctly arrived or not. Then there is another field of 32 bits called acknowledgement number, or ACK, that will give us the next segment we are waiting for. I give you an example. Imagine that we have the same situation, host A, host B. This is the time. And I send from A to B one segment with a sequence number equal to 0. Okay, and this TCP segment has a length of 1000 bytes. Then B will answer with another different sequence number and ACK equal to 1000. That means that, okay, I have received your TCP segment with sequence number 0 and I'm waiting for the next one, which is 1000. So if A sends a new TCP segment, the sequence number will be 1000. So in this case, A knows that the segment with sequence 0 has correctly arrived, thank you to the ACK number. The next field with 4 bits is header length. Is it necessary to have this field? Yes, because as you can see, there is an option field here. So there is not a fixed header, it's a variable header. The next 4 bits are reserved for future use. But since 81, around 40 years have passed and they are still under review, let's say. Then we have 8 flags, 8 bits, these ones, so 1 bit for each flag. The first one is congestion window reduced, in order to know if the congestion window has been reduced. We will see it later in the congestion control mechanism. The next field, the next flag is ECE, so explicit congestion notification. So this is also for congestion. The third one is urgent. It's a flag that if it is set to 1, it means that the segment contains urgent data. Flag ACK is included in all the segments that are acknowledging something. For example, this one that is sent from B to A has ACK active. PSH flag stands for push data. So the segment contains push data. It means that the segment must be sent as soon as possible, even though the full size is completed. So we have to send it as soon as possible. Flag reset, if it is set to 1, it means that the connection must be aborted, must be reset at this moment because a big problem or because Control C pressed by the user. It's a mandatory action to be done as soon as possible. And finally, the SYN and the FIN flags are used for starting a connection, the SYN, and finishing a connection, the FIN flag. So in the next slide, you have all the explanation. We have a fixed header of 20 bytes, but we can have options plus padding in order to reach to the 32 bits of the word in the header. So the first two fields are source and destination port with this length, from 0 to 65,535. This is the maximum number for a port. Sequence number in order to identify a segment, but at the end is the position in the data of the first byte belonging to the segment. ACK number, so it refers to the next segment I'm waiting for, which is the same as I say, I have received up to this number, so I'm waiting. I have not received up to this number. I have received up to the previous number, and the number I'm sending you inside this field is the one that I'm waiting for. So your next sequence number will be this one. Header length. Number of 32-bit words of the header. Is it really needed? Yes, because it's optional to have option in the header. Reserved bits all set to 1. Receive if future use. The flags. The window size. Okay, I'm going to give you an example about the window size. We have the two hosts, A and B. B has a buffer of 4 kilobytes, 4 slots of 1 kilobyte. For example, A sends 1 kilobyte here. So B has to answer with this window size equal to 3 kilobytes. That means that I have 3 kilobytes free. This is the usage of the window size. Or if we have a window equal to 0. Okay, let me remove this example. And then imagine that at this time the buffer is full because I have received something, imagine. And then B is not able to accept anything else. It has to say, okay, my window is 0. It means that I have no space in my buffer. Where and when we'll have to have free space when the application tell me, okay, I can read the full buffer, or I can read 1 kilobyte. Okay, the buffer now is different because the application told me that I can use this this buffer, I can read this buffer, and then imagine that the application read a couple of kilobytes. They are free, so I can notify A that the window is now 2 kilobytes, and A will be able to send new data if possible. The checksum field, it's a field for checking errors of the header, but the difference with, for example, IP is that we have to combine the header, the data, and a pseudo header that is not sent, but it must be used for accessing the checksum. So the difference between IP and TCP in terms of checksum are: in IP, we only take into account the header, but on TCP, we take into account the header, data, and pseudo header. That is not sent, but is used for the TCP checksum. And finally, we have a field called urgent pointer that is related to this bit, this flag. If it is set to 1, it means that, okay, we have urgent data inside the segment. So there is a portion of data inside the segment that must be treated with priority. And this pointer will say, okay, if this is the segment, the header, the data, this is the point where the urgent data starts. In this slide, we have the type of pseudo header that is used for assessing the checksum of TCP. Remember, this pseudo header is not sent. It's only used for assessing the checksum. We have the source IP address and the destination IP address. Okay, you can think again on the violation among layers. So we are working with transport layer. Why are we using IPs in this case? So this is another example, like in NAT or in other situations where the independence between layers is not respected. And here we have on number 0, number 6, and the length of the TCP segment. So with all this data, we can assess the checksum at TCP. Remember, checksum, TCP, header, plus data, plus pseudo header. Why value 6?